This is a quick revision of Topic 6, AQA GCSE Chemistry, Rate and Extent of Chemical Change. So what is a rate of a reaction? The rate of a reaction is how fast reactant can change to give products. There are some slow reactions like rusting, and there are also fast reactions like burning of fuel and explosion. You can represent the rate of the reaction graphically, so you can find the speed of the reaction by recording the amount of the product formed or the amount of reactant used up over time. And then you can represent your data in a graph of amount versus time, and that will give you the reaction rate graph. So this is some representation of some reactions and how the graph will look different if the reaction becomes faster. So as you can see, the steeper the line of the graph, the faster the reaction. And also if we have more reactants and faster reaction, then the graph will look different. The flat line at the end shows that the reaction has finished. You can calculate the rate of the reaction either by measuring the amount of the product that has been produced or the amount of the reactant that has been used up over time. So the rate of the reaction is either amount of reactant used over time or amount of product formed over time. The amount can be measured by the mass in gram or volume in centimeter cubed, the time in seconds. So gram per second or centimeter cube per second. Also, the amount can be measured in terms of moles, and then the unit of the rate will be mole per second. You can also find the rate of the reaction graphically, and you can do this by simply drawing the graph of the which represents the change in the amount of product formed over time or the amount of reactant used up over time. And then to measure the rate of the reaction at a certain point in time, you can draw the tangent at this certain point, and then you can calculate the slope of that tangent by calculating the change in y and change in x. The slope or the gradient of the tangent will be the change in y over the change in x, and that's the rate of the reaction. There are some factors that affect the rate of the reaction. So according to the collision theory, chemical reaction can occur only when reacting particles collide with each other and with sufficient energy. So any factor that will change the rate of collision of a particle or increase the rate of collision or would increase the energy with which particles collide with, then will increase the rate of the reaction. Remember that there is always a minimum energy that is required for the reaction to start, and this is called the activation energy. So activation energy is the minimum amount of energy needed and which is sufficient or which is enough to break the bonds in the reactants to start the reaction. So these factors will include the concentration in case of solution or pressure in case of gas, surface area, temperature, and the use of catalyst. So let's start by discussing the increasing temperature effect on the rate of a reaction. So if the temperature increases, then there is an increase in the rate of the reaction. The reason for that, if temperature increases, that means particles will move faster and then the particles will collide with each other more frequently. So there is more frequent collision between the particles. Also, increase in the temperature means the particle will have more energy, and then there is also an increase in the overall energy. So increasing temperature will increase the number of effective collision and will increase the rate of the reaction. The second factor is the pressure in case of gases or concentration in case of solutions. So if a solution is more concentrated, that means there are more particles knocking about in the same volume of the solvent. And when the pressure of a gas increase, that means we have the same number of particles occupying a smaller space. So both of these will make the collision more effective, will increase the rate of collision. So more frequent collision will take place if we increase the concentration of a solution or the pressure of a gas. The third factor here is the increase on the surface area. So if you break a solid up into smaller particles, that will increase its surface area. So now the surface area to volume ratio will increase. And for the same volume of the solid, the other particles will have more surface area to work on. So that means more frequent collision. So increasing surface area will have effectively more collision and will increase the rate of the reaction. The last factor is the use of a catalyst. The use of a catalyst will increase the rate of the reaction. A catalyst is a substance that will speed up the reaction without being used in the overall reaction. So they are not part of the reaction equation. They will do that by um, driving the reaction through a different pathway that has a lower activation energy. So if we look at the energy change for a reaction, and then for the normal reaction without the use of the catalyst, we have a high activation energy at a certain pathway, but with the use of the catalyst, it will adapt a different pathway with a lower activation energy. So the lower, because of the decrease in the activation energy, the more the particle collision will be more effective, will have more energy, or the activation energy is lowered, and so the rate of the reaction will increase. Reversible reactions. In some chemical reaction, the products of the reaction can react to produce the original or reactants. These are called reversible reaction. So in reversible reaction, we use this symbol instead of that one to represent these type of reactions. Example of these is the Haber process, where hydrogen and nitrogen react together in a reversible reaction to give ammonia. So reversible reaction will always reach an equilibrium if the reaction occurs in a closed system. And a closed system is the system that doesn't allow the escape or the introductory of any other particles during the reaction. So when a reversible reaction occurs in a closed system, the equilibrium will be reached when reaction occurs at exactly the same rate in each direction. So if we have a reaction like this where A and B react to give C and D, we have the forward reaction and we have the reverse reaction. The reverse reaction when when the products react together again to give the reactants. So at the start of the reaction, the reactants will start to react together, and that means the concentration of the reactants will decrease, and then that means that more products will be formed, and the rate of the forward reaction will start to decrease because of the concentration decrease of the reactants. The concentration of the product at the same time will start to increase. That means the rate of the reverse reaction will start to increase, and that means the rate of the reverse reaction will increase. That will continue until the reaction reaches an equilibrium. At equilibrium, both the forward and reverse reaction will occur, but at the same rate. The concentration at equilibrium of all reactants and products will remain constant. They will not be the same, but they will remain constant. The concentration, as we said, of reactants and products are not the same at equilibrium. They will remain constant, but they will not be the same. So the position of equilibrium can be either to the right or to the left. When we call the equilibrium position to be to the right, that means more products are produced, or the concentration of the products are higher than the concentration of the reactants. And if the equilibrium is to the left, that means at equilibrium, the concentration of the reactants are higher than the concentration of the product. The position of the equilibrium will depend on certain conditions. These are temperature, pressure in case of gases, and the concentration of reactants and product. Le Chatelier principle will talk about how these factors affect the position of equilibrium. So according to Le Chatelier principle, if a system is at equilibrium and there is a change in any of the conditions, then the system will respond to counteract that change. So if the concentration is changed, so let's look at this reaction. Will A and B react to give you C and D? If the concentration of one of the reactants or product is changed, according to Le Chatelier principle, the system is no longer at equilibrium and the concentration of all the substance will change until equilibrium is reached again. So if the concentration of the reactants like A or B is increased, then the system will now try to respond by trying to decrease the concentration of the reactants, and thus that means the concentration of the product will increase because that will force the reaction to go to the forward pathway. So the forward reaction will be higher, or the rate of the forward reaction will increase and more product will be produced until the equilibrium is reached again. If the concentration of the products like C or D increases, then the system will respond by trying to reduce the concentration of the product to get back to the equilibrium, and that means the concentration of the reactants will increase because the reverse reaction now will have a higher rate. So now the system will respond by enhancing the reverse reaction, and the reaction will be shifted more to the left. The second factor that can affect the position of equilibrium is the temperature change. Again, for a reaction A and B that will give you C and D, we know that there are two possibilities for any reaction. The reaction can be either an exothermic reaction or endothermic reaction. So if one direction of the reaction is exothermic, then the opposite direction will be endothermic, and that makes sense because whether reaction is exothermic or endothermic, that depends on whether the reactants or the products have the higher energy. So if the forward reaction is exothermic, that means the reverse reaction is endothermic. Exothermic reaction will lead to an increase in the temperature of the system, and endothermic reaction will lead to a decrease in the temperature of the system. So until they reach equilibrium. So at equilibrium, the temperature will be constant. So if the temperature is increased, the equilibrium will moves in the direction to try to decrease the heat, which means that it will try to re-establish the equilibrium. So that means it will enhance the endothermic reaction, so the reverse reaction in this case. And if the temperature is decreased, the equilibrium moves in the direction to try to produce more heat, so trying to enhance the exothermic reaction. So as more specific example, where the exothermic reaction is the forward reaction, the reaction will go as follows. So if the temperature increases, there will be an increase in the rate of the reverse endothermic reaction, which means we're going to have more reactants, less product, and lower yield. And if the temperature decreases, that means there is an increase in the rate of the forward exothermic reaction. So we're going to have more of the products and more yield. So you can control the yield of your reaction by controlling the temperature of your reaction. And finally, the effect of pressure change on equilibrium. Increase in pressure means that we have the same number of particles occupying a smaller space. And the increase in pressure will favor the reaction that produce the least number of molecules. So if we look at the following reaction, well, nitrogen reacts with hydrogen to give ammonia, you can see that on the left hand side where the reactants are, there are 4 moles overall, and the right hand side, which is the product, there are only 2 moles of the ammonia. So If the pressure is increased, the equilibrium will shift to the side of the equation where fewer moles of the gas are produced. So if you increase the pressure, equilibrium in this case will move to the right because there is a least number of moles of the products. So more products will be produced in this case. And if the pressure is decreased, the equilibrium will be shifted to the side of the equation where more moles of the gas are produced, meaning more of the reactants. So we're going to have less of the product and less yield.